Greetings. So, we have the fourth module in this series of lectures on classical mechanics, which are condensed lectures. So, we don't derive any relation in great details, but I'll take you through the major steps. And today we will discuss rotations and angular momentum. We will also introduce the moment of inertia tensor and the Euler Angles and the Euler Equations, of course. So you need this whenever, for example, you have this plane flying and you want to turn it, okay, on its flight. It has to turn about, there are various alternative axes. And there are three orthogonal axes about which you can turn the plane. And you need very precise measurements so that you can operate this machine. It's a great machine, but there is so much of electronics that goes into it. And there is so much of mechanics that goes into it. So we need a good handle on what rotations are about, how to bring them about, what is it that controls rotations. How do you analyze the equation of motion when you consider angular displacements with respect to time and so on. And let me quickly recall that we discussed this in one of our earlier discussions, that if you have an equation of motion and whenever you have a radial force, okay, the angular momentum is conserved. And we discussed it in the context of conservation of angular momentum as a conservation principle, which is immediately connected with the invariance with respect to angular displacement. So there is a symmetry with respect to rotations, and the quantity which is conserved in the spirit of Noether's theorem is the angular momentum. So we are going to talk about rotations and angular momentum in this unit. And when you talk about angular momentum, you must talk about angular momentum with respect to what? Okay, so this ball which is being kicked around, it has got a certain angular momentum with respect to different points on the playground. And the angular momentum with respect to different points on the playground are obviously different, because the position vector r with respect to each point of origin is different, right? And in addition to this motion, you see that the ball is also spinning about an axis through itself. So there is an additional rotation, which is a spin rotation about this axis. And you can talk about the orbital angular momentum and also the spin angular momentum. There are two kinds of rotations which are involved in this. And the net angular momentum will be due to the orbital motion, which is about some point, and also because of spin, which is about an axis which is going through the center of mass, for example, right? So there are these two motions that you have to consider. And if you have something like an orbit, this chair has come in an orbit, right? If you see how it has come, right? So it is coming along a certain orbit. But as it does so, it is also spinning about an axis through itself. So this is just the kind of motion that you described when you were talking about the soccer ball, which was spinning as it was being kicked around. So what is peculiar about this chair is that it is a rigid body, okay? And no matter what happens in its transit or how it spins around, the distance between any 2 points on the chair remains the same, okay? So no matter how it spins, if you take any 2 points on this chair, that distance remains the same because it is a rigid body, which means that the number of degrees of freedom that the particles of the chair has are brought down because of this constraint. There is this constraint that the distance between the two particles must remain the same, and it is very easy to understand this when you just consider two objects, two particles. If you want to describe these two particles, if they had nothing to do with each other, then you would need three coordinates for one and another 3 for the other, a total of 6 coordinates. But then if you know that they are bound by a certain rod, so that the distance between those two particles always remains fixed. So there is one constraint, and then it is no longer necessary to specify the 6 degrees of freedom. You can specify less, because if you just specify the coordinates of one point, this is particle 1, then the position of the other particle is completely fixed by pinning down the position of this particle, first particle, and then these two angles delta and lambda. So with these two angles and the 3 coordinates of P1 with 5 degrees of freedom, you can specify the 2 particles if they are constrained by a constant distance between each other. Okay? Now, if you add a third particle, then how many parameters will we need? So in the first place, you should recognize that these 2 objects are completely specified by 5 degrees of freedom, 3 of which x1, y1, z1 are the coordinates of particle P1. So they have got, x1 has got the dimension of length, y1 also has got a dimension of length. But delta and lambda, these are 2 angles, they don't have the dimensions of length, these are angles. Okay? So the 5 degrees of freedom that you are supplying over here are not necessarily those which have the dimension of length. So if you then subsequently study the velocity, the rate at which these degrees of freedom are changing, then dx by dt will have the dimension of length over time. But d delta by dt will not have the dimension of length over time, because delta does not have the dimension of length, right? Delta is the angle. So you have to remember that these degrees of freedom are not necessarily having the dimensions of length, and their velocities will not have the dimensions of L t to the minus 1. And we are now talking about the possibility of placing a third particle which is at a constant distance from P1 and also from P2. So where can you place it? Where in this 3-dimensional space can you now put a third particle so that it will have a constant distance from P1, which means that it can be anywhere on the surface of a sphere centered at P1 at that constant distance, but it should also have a constant distance from P2, which means that it should also be on the surface of a sphere which has its center at P2 and whose radius is that constant distance that we just now talked about. In other words, it will have to be on the intersection of these 2 spheres. Okay? So we construct these 2 spheres. So this is the question we are trying to address: where can we place this third particle? And we determine this intersection of the sphere, and the intersection of the sphere will be this circle. Okay? And on the circumference of this circle, you can place this particle anywhere. So it has got only 1 degree of freedom, okay, which you can express as some sort of an angle from the center of the circle in the plane. You can determine, you can think of some reference axis, and that single degree of freedom will be required to pin down the third particle. Okay? So now you were left with only 1 degree of freedom, and any additional constraint that you can put. For example, you ask, where will you keep a fourth particle which will be at constant distance? It can only reduce it. It can only reduce the degrees of freedom, and you were already down to 1. And if you reduce the degree of freedom from 1, where do you go? 0. Okay? So the 4th, the 5th and the 6th and so on, no matter how many particles you have got, you are not left with any additional degree of freedom. So the complete rigid body is completely described by just 6 degrees of freedom, the 5 for the 2 particles and then the 6th for the third particle, and beyond that you are left with no additional degree of freedom. So if you just specify 6 degrees of freedom, the complete rigid body, its orientation, everything is completely pinned down. And these degrees of freedom need not have the dimensions of length. Some of them may have, some of them may not have. Okay. And this is not the only way in which you can get those 6 degrees of freedom. You can get it in some other way, alternative ways also, but it is not going to be anything more than 6 and it will not be anything less than 6. So this is how you characterize a rigid body, and then we talk about its rotation. Its rotation about some point, and during its rotation it may have a spin about itself, like the soccer ball or the chair that was tossed. Okay. So the net angular momentum of a mass distribution, no matter what that mass distribution is, it may have some regular shape like the soccer ball, it may have some shape like a chair which does not have any particular geometry, and if it is a broken chair, it only gets worse, right? So irrespective of what the mass distribution is, it can be a piece of rock with arbitrary shape, right? The net angular momentum about some point will be given by the integration now, because we consider this mass distribution to be extended and not discrete. So you will carry out integration of every mass element, and if there is a mass rho times the volume element, you have to add up all of this, and this is what generates this integral. This density of course can change from point to point, so which is why the position vector of that particular point appears as an argument. In some cases it may be uniform, but it may not be in some other situations. So now you can split this total angular momentum in these two components, the orbital angular momentum and the spin angular momentum. Okay. And if you look at the spin angular momentum, you have this r cross v, from which you will get this r cross omega cross r. So this is the spin angular momentum. Okay. And if you now expand this cross product, this is the triple product, the vector triple product. There are two terms, one coming from r square omega, and the other is when you subtract the r dot omega times r. So this is nothing but the expansion of this triple product. So you're looking at the spin angular momentum. Okay. Now this terminology gets carried over also into quantum theory, but you have to be very careful, because in quantum theory you do not have any classical analog. So you should not carry the sense of rotations, orbits and spin into quantum mechanics. So that will have to be correctly interpreted. We will discuss this in further details when we have a formal discussion on quantum theory. But at this point, I would like to alert you that you should be very careful in carrying these ideas into quantum mechanics. In quantum mechanics, you do not even use the position and momentum together. They are not measurable. So the question of using r cross p to define angular momentum does not arise. Angular momentum has to be defined in a very careful and different way in quantum mechanics. So you have these two terms in the spin angular momentum, and this has got a very interesting upshot. Look at the first term. The first term is an integral in which you have got an angular velocity over here, and this may be, even in the case where it is constant, even if it is not changing with time, you can possibly pull it out of the integration, this thing, and that will give you a component of the spin angular momentum in the direction of angular velocity. But the second term has got an integral over this, which means that the angular momentum and the angular velocity need not always be collinear. They may not be parallel to each other. And this is an idea that we have to be really comfortable with, that we normally assume that the angular momentum and the angular velocity have got the same direction. It is obviously not so. Okay, so there can in general be an angle between these two, and we have to handle these two terms carefully. So the first term, you have got r square, which is like x square plus y square plus z square, if you like, in Cartesian geometry. And in the second term, you can expand this r dot omega as the sum of the product of the corresponding components, right? And then you have got the position vector r, which is expressed in a certain coordinate system Ex, Ey and Ez. And notice that you will get a quadratic term because this x times this x will give you x square times omega x in the direction of Ex from the first term, right? And you have a corresponding term x square times omega x Ex from here. But this comes with a minus sign. And the same thing will happen with the corresponding y and z components. So the quadratic terms in the second term cancel the corresponding terms in the first. Okay? And then you are left with the remaining terms. Okay? So there is this symmetry because of these quadratic terms, and those are the terms that get cancelled out, and the remaining terms will add up to give you the components of the spin angular momentum along x, y and z coordinate system, and they will be given by these integrals. Now this is a fairly messy integral to work out. Depending on the shape of the object, okay, you have to integrate y square plus z square. And the coordinate of y and the coordinate of z and what is the density at that point, okay, this can add up to very complex integrals. And you have to take all of this into account, and we develop a compact notation to write them. So these integrals are quadratic, but they do not have anything in x. So this is labeled as ixs, xx, this as iyy, and this is izz. And then of course there is some symmetry between these two terms. They turn out to be similar, but they come in products with the components of the angular velocity, which are omega y here and omega x in the second. And similarly, there are two other terms which are one with omega z and the other with omega x. And then there are another two terms. Okay, so there are these 9 terms which are called as the components of the moment of inertia tensor. Okay, so you can write the spin angular momentum using this compact notation ixx, ixy, izx. So they come over here, and you have got components along ex, ey, ez, and you can interpret this as the component of the spin angular momentum about the x-axis. Okay, so this is the component of the spin angular momentum about the y-axis, which is the sum of these 3 terms. So the moment of inertia tensor, which is made up of these 9 coefficients, this not only depends on the mass distribution about a certain point, okay, it also depends on which coordinate frame of reference is being used to describe these integrals. Because if you rotate this, obviously the components along x and y change. Okay, that is what makes the position vector a vector in the first place, because a vector is defined as a quantity whose components transform according to the cosine law when you rotate a coordinate system. So about different coordinate systems, you will have different components. So the moment of inertia tensor will be specific to a particular orientation of the coordinate system. So it is a second rank tensor, okay, and it has got this important property that it depends on the mass distribution about the point about which the object rotates, and also the specific orientation of the coordinate frame of reference which is being employed. So now when you look at this equation, and this is a matrix equation, notice that in general the angular momentum, the spin angular momentum and the angular velocity in general will not be parallel to each other. Okay? So this is an important conclusion, and all studies of rotational motion have to take this into account. When you work with point particles, there is no mass distribution because all the mass is concentrated at that particular point, but that is not so with extended objects. So if you carry out the same kind of analysis with the rotational kinetic energy, we did it with the angular momentum. You can start with the expression for the rotational kinetic energy from first principles. You will arrive at this relation, and I leave that as an exercise. It will be a scalar, of course, but a scalar which will result from the contraction of this matrix multiplication involving tensors. Okay, so the moment of inertia is the tensor of rank 2, and the angular velocity is a vector. Actually, it is a pseudo vector of rank 1. So from this contraction, what you get, of course, is a scalar. And now that this moment of inertia tensor has got components, there are 9 terms, but you can find a coordinate system. You can rotate the coordinate system in such a way that the moment of inertia tensor is diagonalized. Okay, so if the matrix is can be diagonalized, which is not always possible, depending on the singularity and that type of considerations, you can find an eigenbasis in which the matrix can be diagonalized, and you can develop an expression for the moment of inertia tensor matrix as a transformed matrix in which you carry out this transformation, which is the diagonalization, this thing. So this is the transpose of the matrix, and you can carry out a diagonalization process. And once you diagonalize it, instead of having these 9 components, you have the 3 principal components. So these are the 3 principal moments of inertia about the principal axis, which are those axes which you get after you carry out this diagonalization. And when you diagonalize the moment of inertia tensor, you will also carry out a corresponding transformation of the basis set. So if you have Ex, Ey, Ez, then this will get rotated to Ex prime, Ey prime, Ez prime, and this new basis is the one in which the moment of inertia tensor will be diagonal, and it will have these diagonal elements which are I1, I2 and I3. They may be equal to each other in some situation, but by and large they will not be so. So if they are equal, you can pull it out of the matrix and write it as one that multiplies a unit matrix. So the same transformation which affects the diagonalization of the moment of inertia tensor will also transform the components of the angular velocity vector omega x, omega y and omega z to omega x prime, omega y prime and omega z prime in the new basis, which is Ex prime, Ey prime and Ez prime. So this is the rotated basis. Okay, what you may call as the rotating coordinate frame of reference. It is bound to the rigid body, right? And this is the eigenbasis in which the moment of inertia tensor will be diagonal. Now, you can write the angular momentum now in the rotated basis. So its components will be given by this, right? And this is, however, now a diagonal matrix, right? After you carry out the diagonalization. So you have the components of the angular velocity in the eigenbasis in the rotated basis. You have the components of the angular momentum in the rotated basis, which is the principal basis or the eigenbasis that you may call it as. And then this angular momentum components in the basis x prime, y prime, z prime will be given by this, and it still doesn't guarantee that angular momentum will be parallel to the angular velocity. Okay, it will happen only in some particular cases, okay, because in general I1 and I2 and I3 are not equal to each other. These are the components of the moment of inertia, the principal components of the moment of inertia. Okay? So in general, the angular momentum velocity, angular momentum and angular velocity will not be parallel to each other, and there will be some angle between them. So it will be 0, this angle will be 0 if these three moments of inertia are all equal to each other, right? Or if two of the three components of angular velocity are 0. Okay? So that will be a special situation in which you can have the angular momentum parallel to the angular velocity. So these are the only two situations when this can happen, not otherwise. So let's take an example. We consider a cube and we consider it to be rotating, let's say, about the x-axis, and we locate this x-axis, the coordinate frame, the ex, ey, ez, so that the coordinate axes are respectively parallel to the three edges of a cube, all right? And the origin is located at the center of a cube. Now this is, you obviously do not expect it to be the eigenbasis, okay? And you can evaluate what the moment of inertia of this cube will be about this origin when you choose this coordinate frame of reference. So how will you get it? This is the matrix that you have to determine. And when you determine all the matrix elements, you will get the moment of inertia. So what we have to do is to evaluate these integrals, right? And we can evaluate these integrals for the cube. So if you assume that the cube has got uniform mass density, let's take a simple example. Then for that uniform mass density, you have to sit down and evaluate all of these 9 integrals, okay, some of which are symmetric. So the actual number of integrals is reduced. It is reduced from 9 to 6, okay. So you have these 3 and then 4 and this 5 and 6, okay. But these 6 integrals you have to evaluate to get the 9 elements. So let us see how one of these integrals is evaluated. Let's look at Ixx. Then you can evaluate, these are independent degrees of freedom, so you can carry out the integrations independently of each other, right? So you will have rho coming from here, then you have an integral y squared dy going from 0 to a, which is the length of the side of the cube. So you will get a term in y cube over 3 from this integration, but the integration limits are 0 to a, so you will get like a cube over 3 there, and from the other two integrals you will get a and a. So you get, if the density is uniform, rho is nothing but m over a cube, and then you get the a and a from the integrals over x and z, and then you get a cube over 3 from the integral over y squared. So you get this term, right? So you can evaluate the remaining terms, and once you evaluate all of these integrals, you can get the moment of inertia tensor, which will have this particular structure. So you can determine all the remaining integrals the same way, okay? And you can go ahead and diagonalize it. So I will leave it as a simple exercise to diagonalize this matrix. Then the diagonal elements turn out to be 1 over 6, 11 over 12, and 11 over 12. So notice that they are not equal to each other, but 2 of them are equal to each other, okay? And if you take the sum of the diagonal elements, in both cases it will be the same, because the character of a matrix remains invariant when you carry out this similarity transformation, which is what is involved in this diagonalization, okay? So you get this diagonal elements, and the same matrix which diagonalizes the moment of inertia tensor will give you a new basis, which is not ex, ey, ez, but it is ex prime, ey prime, ez prime. So that is the rotator. It is bound to the rigid body. It is the eigenbasis. of along which you have got the principal axis of the rotating body. Okay? So one of them will be along the body diagonal, so along the body diagonal OO prime in this figure, and the other two axes will be orthogonal to that, in the plane orthogonal to that, but in that plane it can be anywhere. Okay, so it doesn't matter because they are completely equivalent to each other, but it will be orthogonal to this plane. So one axis is orthogonal to this plane, which is along the body diagonal OO prime, and the other two axes can be rotated. It doesn't matter what they are, but they are completely equivalent. So those are the three principal axes of this cube, and in general you will not have angular momentum spin, angular momentum to be collinear with the angular velocity. But if the cube is rotated about one of the principal axes, okay, then the other two components of the angular velocity will be 0, and if you rotate the cube along this principal axis, then you will have angular momentum to be parallel with the angular velocity. So you can think of different objects. The analysis is somewhat easy for those objects which have got some kind of symmetry, like the cylinder, but in general it is not very straightforward. And then the motion is described by very complicated equations, which are the Euler equations. Okay, because the angular momentum would change, and it can change only when there is a torque which is applied on the body, and then how the different components change is described by this relation. So you will remember that the time derivative in a laboratory frame of reference or in an inertial frame of reference is not the same as the time derivative in a rotating frame of reference. So we discussed this at great length when we reconciled with the need for using pseudo forces when we describe motion in a rotated frame of reference. So we came across terms like the centrifugal term, the Coriolis term, and also the leap second correction. Okay, and we recognize how and why these terms are important. And the operator relationship that we discovered, which connects the time derivative in the rotating frame of reference, like this object is at rest in our frame of reference, but it is not at rest in the frame of reference in which the earth itself is rotating. Okay, so in our frame of reference, because we are rotating with the earth, this desk and this object is at rest. So the two time derivatives are not equal to each other, and the relationship between them is given by this operator equivalence, which we deduced in one of our previous classes. So if you apply this operator to the angular momentum, you will get an expression for the physical torque. Okay, and the physical torque is equal to the cross product of omega with L. Okay, and then there will be a rate of change of angular momentum in the rotating frame itself. Okay, so the dl by dt, which is torque, which you perceive in an inertial frame, is different from what you do in a rotating frame. So just the way you have got the real physical interactions which govern the Newton's laws, which account for the change in momentum dp by dt, right? But if you examine the motion of that object, if you examine how the equilibrium changes in an accelerated frame of reference, then you must come up with pseudo forces. So here you will have to come up with pseudo torques. Okay, because dLr by dt prime is the torque that you would think is operating in the rotating frame of reference, but it is not equal to the torque in the inertial frame of reference. The difference is in this cross product, and it is coming entirely because you are carrying out this analysis in the rotating frame, which is the eigenbasis for the object in which the moment of inertia of tensor has got diagonal elements. So there is some convenience that you get out of it. but the price to pay is that you must use pseudo torques. So this relationship is a vector equation. It is known as the Euler's equation. You can write it for the three components and you get three scalar equations, which are also called as Euler equations. So you can write the Euler equation either in the vector form or in terms of its components, and you have got corresponding three scalar equations. Okay? So these are the Euler equations, and you have got the sum of these two terms. So this is the first term, which is the blue term, which is the cross product of omega and L. So I determine this cross product in the eigenbasis of E1 prime, E2 prime, E3 prime. The primed frame is the eigenbasis. So in this, I can express this cross product, and in the same frame, I can write this expression for the pseudo torque. Okay, so I get these three components, right? And then you add up these two to get the physical torque, and the physical torque is now given by these terms. So you have got the first matrix is coming from the blue term, which is this, and the second is coming from the red term, which is this. And the sum of the two is what is involved in the Euler equations. So these are the same equations, there is nothing new about it, but we are writing the Euler equations in different forms so that we can solve this. Okay, so these are the Euler equations, and you can write this L3 prime, L1 prime and L2 prime because we know that these are components of the spin angular momentum in the rotated frame of reference. So these we know are given by I3 omega 3 prime from here, right? The third component will be given by this, and you can write these components L3 prime and L2 prime in terms of the principal components of the moment of inertia, I1, I2, I3, the small I1, small I2 and small I3, which are the diagonal elements, and the three components of the angular velocity in the principal basis. So what is interesting is that only the diagonal form of the inertia tensor is required. So objects which have got different shapes and different mass distributions, as long as their eigenvalues of the moment of inertia tensor are the same, they can be written by the same Euler equation of motion. So it really provides a great simplification in solving rotational dynamics. Okay, so the object can have any different shape, but then they should have the same principal moments of inertia. So and as long as they have the same, they are described by the same, essentially the same Euler equations. So now we consider a simple case in which there is really no torque acting on the body. So the left hand side is 0, the right hand side better be 0, but the right hand side is a difference of two terms. So the first difference must be the negative of the other, right? So you have this term to be negative of this, and when you write one term to be the negative of the other, and this is the torque that you think is what is changing the angular momentum. But the angular momentum is not really changing in an inertial frame of reference. It is changing in the rotating frame of reference because the observer is rotating, not because the angular momentum itself is changing in an inertial frame of reference. So this is the pseudo torque. So this has got interesting consequences. For example, if you have an angular momentum, its time derivative will be given by two terms because its direction can change, dl by dt, and its magnitude can change, which is this dl by dt, right? Because any vector is a product of its magnitude and direction. So the change in that vector, the rate of change in that vector, will be given by the sum of these two terms. So what is very interesting is that if you have a a heavy mass which is spinning about an axis, okay, and this is a nice video by this Australian fellow. It is there on this his YouTube channel, so the reference is given over here. You can see this video. There are several videos of this kind which you will find very easily on the internet. This is one that I liked, and you have a 20 kilogram mass, which is huge. All right, means when you travel typically with a 20 kilo suitcase, right, you don't lift it so easily, right? And here is a 20 kilo mass, it's a wheel, and he's holding it so easily. He won't be able to do it if the mass was not spinning. But when it is spinning, okay, if you set it into rotation, and the YouTube video shows how his friend comes and imparts a spin on this wheel, and once that spin is imparted, then you can see that because of the torque due to gravity, the direction of the angular momentum will have to change. The magnitude of the angular momentum may not really change, because that will really involve also a change in the rotational kinetic energy, and that is not going to happen unless you also impart some energy to it, right? But the direction of the angular momentum changes, and he can turn this whole thing. It almost looks like anti-gravity, but please remember, it is not anti-gravity, it is actually gravity which is enabling this. It is the torque due to gravity which forces the direction of the angular momentum to change, and as long as he allows that to change, he is not going to experience any trouble, right? So this is the gyroscope precision. So the gyroscope precision is described by this equation, and notice that if you take away all the you take away this magnitude, bring it to the right, but when it comes to the right, it comes in the denominator. So you've got this Zmg over this angular momentum, which is I3 omega, okay, in the eigenbasis, in the basis of the rotating body. Then the direction of the axis along which the object is rotating is time dependent, and this dot denotes the time derivative of this unit vector. Okay, so its time derivative is not 0. It is, as you can see, the right hand side has got this cross product, so it is in the direction which is orthogonal to both E3 and E3 prime, and a change in the unit vector is always orthogonal to it. So that is quite in line with this, all right? And this is what causes the precision of the gyroscope. Now this will happen because there is a weak torque due to the gravitational field of the Earth, which is causing this precision. So it is not anti-gravity, it is actually gravity which is making this happen, okay? But it looks like gravity because otherwise there is no way you can hold a 20 mass object like that. Try to do it even with a much smaller one, okay? Even if you have a stick which has got just 1 kilo at its end, and try to raise it at that angle, and it's not going to be really easy. Maybe you can do it, but but otherwise it's not really easy, okay? And 20 kilo wheel, even harder. So that is going to happen to a top, okay? Because once you have a top spinning, okay, at some point, if the top gets slightly tilted from the local vertical, okay, if it gets slightly tilted from the local vertical, then this torque will make the direction of its angular momentum precise. Now that happens even with the Earth, because the Earth is also subjected to some gravitational fields. It's not just the sun, but there are forces due to other objects in the planetary system, in particular the moon, right? And when you have these two forces, or more. If there is a single force, it will always be along the radial line, and there will be no torque. Angular momentum will be conserved. But when there are two forces along different lines, there will be a net torque. Okay? So the sun and the moon together, and then to make matters worse, there are other objects in the planetary system, in the solar system. The Earth would also be precessing, and it takes like 26,000 years for the Earth's axis to precess and complete one full rotation. Now this is a very interesting astronomical event, right? So it takes 26,000 years to complete this 360 degrees. So over a human lifetime, which is 70, 80 years, all right, it takes about 72 years that the direction of the pole will shift by 1 degree. And over centuries, this effect will accumulate. And over thousands of years, even more so. Over 26,000 years, it will complete one full rotation. So what you think is the dhruva, which is the pole star, is not always the pole star. It will keep shifting, okay? And over your lifetime, it will change over a degree. So here is a picture of how it changes. So now you identify the pole star by looking at this great bear. It typically points toward the pole star, the Polaris, which is over here. But then 2,000 years ago, the Earth's axis was pointing somewhere over here, and another 2,000-3,000 years prior to that, it was pointing toward Tubin, and another, like 10 or 12 or 13,000 years from now, it will be pointing toward this beautiful star, which is called Vega, right? So the pole star will keep shifting, and this is an amazing. This can actually help you determine the period of some events in history. Mahabharata, for example, means people argue that it probably happened like 5,000 years ago. And if it happened 5,000 years ago, what would be the pole star? It wouldn't be Dhruva. It would be Tubin. And if it was Tubin, then the Earth's axis would be pointing in that direction, and the remaining stars in relation to this would be different. And some of these things are described in beautiful poetry in Mahabharata. It's described in beautiful poetry. It tells you where are the different stars located, how are they oriented in relation to each other. The reason these descriptions were important, because this was used for navigation. Nighttime navigation, they tell you in which direction you should be going if you're going through a forest. Okay, you're not using the compass needle at the time or the GPS, but you were guided by the orientations of the stars. And from the descriptions of the orientations of the stars, you can calculate what the sky would have looked like at the time and try to infer if these descriptions are accurate or when these events would have taken place. So I do not know how reliable these calculations are, but people have indeed attempted to do so. But what is very important is to recognize that the pole star actually, the Earth's axis of rotation is not always pointing toward the pole star. And even over human lifetime, it changes by 1 degree, and over a few generations by several, right? And over thousands of years, you see a different part of the sky altogether, okay? So, in fact, the pole and the pole star, which is actually a binary star, they will be closest to each other in 2102, okay? So, here is a picture from, I think this is from NASA's website, and they demonstrate in this small video how the precession of Earth takes place because of these gyroscopic effects, because of the gravitational fields of other bodies in our own planetary systems, okay, which exert this torque. So this is the gyroscopic precision, but in addition to this, there is also some wobbling because the earth has got an oblate shape, okay, and in addition to the angular velocity, it has got a little bit of nutation because the moment of inertia about the axis is not the same as that in the plane horizontal to that, orthogonal to that through the equatorial plane, okay, because the earth has got a slightly oblate shape. So the difference in the moment of inertia, if you determine the three components of the moment of inertia, two orthogonal components along in this plane, in the equatorial plane, will be equal, but they are not equal to the component along the axis. And as a result of it, there is a little bit of wobbling that takes place, that's like nutation. And this was detected by Chandler, and it is not fully well understood. It is because of the mass distribution within the earth, okay. The oblate shape is the dominant reason. If the earth was a perfect rigid body, it would have a period of like 305 days, but then it is not an exact rigid body. The atmosphere is moving around, there are tidal forces, there are tectonic plates movements and so on. So it's a very complex phenomenon which needs to be studied in some details. It's an interesting area of research. So this is called as the Chandler moment, or Chandler wobbling, okay, as it is called. And now you therefore need to describe these rotations. So any arbitrary orientation of a body. So you have one object with a coordinate frame of reference sitting at this point, and this is your chosen reference frame. But then you can think of any other rotating frame of reference about some arbitrary axis and rotating about some other arbitrary axis, right? So there is a very nice theorem called as Chasel's theorem, which says that the most general dislocation of a rigid body from a given coordinate frame of reference can be described as a sum of two displacements. One is the translational displacement from here to its center of mass, and the other is a rotation about the center of mass. Okay, so these two things completely describe any which way you can change a coordinate frame of reference with reference to what you might call as an inertial frame of reference or a laboratory frame of reference. So in other words, you can think of a screw. So the way the screw would propagate, you can have it along that particular axis, and then a rotation of the screw will give you the rotating frame of reference. So any transformation can be brought down to the rotation of a screw. Okay, so this is called as a screw motion, and this is very useful. The Chasel's theorem is very useful in describing rotations. You can of course choose some other coordinate system, but that will only make your life messy, because the equation of motion will still remain correct, but they will be messy. There will be too many terms to worry about for no reason at all. So now you need these three rotations, and the three easiest rotations are those through the Euler angles. So you begin with the original frame of reference, and you carry out one rotation about the z-axis through an angle phi. So this is the angle phi, and you get to a new frame of reference, right? And now you have got a new x-axis and a new y-axis, but the same z-axis. And now about the new x-axis, you carry out a rotation through an angle theta, okay? And then you have, that will give you a new z-axis, which is this, and about this new z-axis you carry out a rotation through psi. So now you have got this three angles which are the Euler angles, okay? And you already know that the rigid body is completely described by these 6 parameters. So if you get the 3 Euler angles, you're done. You don't need anything beyond it. There are alternate ways in which you can carry out this transformation. So instead of carrying out transformation about the z-axis first and then the new x-axis next, you can choose the new y-axis if you like, right? Okay, so there are alternative and equivalent ways of defining the Euler equation. So there is a certain convention which is involved, but this is a rather common one which I make use of. And with this, we have all the tools to study rigid body rotations, change in angular velocities, change in angular momenta, how the torques are involved in bringing about precisions or nutations or a spin, if you like, because you can have not just a precision about one axis, you may have a nutation about another, you may also have a spin as such. And these are the rotations which are involved in controlling a plane, for example. So there are these 3 axes which I mentioned at the very beginning, and in the context of aerodynamics, it is usually these angles are often referred to as yaw, roll and pitch. That is just the terminology which is used in this context. And all of this is controlled by a good number of gyroscopes which are installed in the plane. They're very sensitive. You change any of these angles even slightly and it will change the angular momentum. Okay? And through the feedback mechanism, you can know if the plane is tilting, is it precessing, is it wobbling, right? So any of these things can be detected by having electromechanical couplings, and this is what is done, this is what is required. A large number of gyroscopes are installed in all moving objects. You can install them in motor cars, for example, because if the car is skidding, okay, then the gyroscope will tell you in which way it is skidding, and then you can have a feedback electromechanical mechanism to control it. So modern life, whether it is flying satellites, rockets, launching satellites which will go to other parts of the solar system, to moon, to Mars or whatever, or flying aeroplanes or even driving cars on the roads, they all involve the use of solving the Euler equations using sophisticated gyroscopes and having electromechanical coupling and feedback mechanisms for safety purposes. So I'll stop here. I can take a few questions. And if there is no question, we will stop here for today.